Okay, welcome back, everyone. So we are going to start our second session today. We will have 3 talks on simulation working group, fundamental physics working group, and waveform working group. As always, as before, we have 20-minute talks plus 10-minute discussion and questions. You're always welcome to post your questions on Zoom, and also you can follow up on those questions on Slack, and other people will be joining the discussion. So for the first talk today, in the second session, I'm happy to introduce Dr. Sweta Shah. She's a postdoc in space interferometry at Max Planck Institute for Gravitational Physics in Germany. And she is the LISA data processing in the LISA data processing working group. Also, she is in the DI committee of the LISA. So whenever you are ready, please go ahead, Sweta. I think you're muted.
Unmute. Can you hear me now?
Yes.
And my slides work, I hope. Let me just stop the video so for the talk.
We can see your slide and your.
Okay, cool. Yeah, thanks a lot, and thanks for this invitation. So I will give an overview of the simulation working group and the INREP working group, which is responsible for the first leg of the data processing step in the LISA data analysis chain. So both of these groups are part of LDPG, of which you have heard about a while ago from Antoine. And I'm sharing the L0 to L1 working group. So it's also called INREP. So I'll talk about that in a moment. So you've seen this slide already, and the idea here is that for simulation group to be able to simulate the noises that you expect in the instrument on board as realistically as possible, and then the objective of INREP pipeline or the L0 to L1 pipeline is to be able to mitigate these noises to the required level, which is basically this sensitivity that we are aiming for. So I will talk about the challenges there and the activities that that involve these two groups. So here's basically a list of well-defined concrete tasks that we have so far in the simulation working group on the left and the INREP working group on the right. So you heard briefly about LISA node. That's the official instrument simulator that is responsible for generating measurement files, which has all these noises that you see on the left. They are listed as tasks, and so the core developers, well, so the creators, so to speak, are Jean-Baptiste and Olaf, and there's a bunch of developers who are working on adding features to realize these noises to more real scenario, real case, and of course, as the first leg of the data analysis, which receives the L0 data and produces the L1 data. So L1 data are these so-called TDI observables, and I'll talk about that in a moment. We interact very closely with the working group, the simulation working group. We interact with them by telling what data we require in order to reproduce, produce L1 data that has noise level mitigated to that is required by the science objectives. So again, in INREP we have also so INREP, by the way, stands for Initial Noise Reduction Pipeline. We have also these tasks that are very well defined, and they're all with the objective to write a solid phase A, let's say phase A, which is until the end of this year for the mission formulation reviews, the reference pipeline that can be verified. And so all of the codes for the simulation and INREP are hosted in Into-P3 GitLab, and of course you have to be in the LISA consortium to get access to this or to become developers. And in INREP we are working in a Scrum team for the pipeline for the reference pipeline that will be hosted in the SOC, which is the Science Operations Center in ISAC. So I will talk about some of the contents of these tasks and the challenges. Okay, so just to recap a bit, the LISA data chain, you've already heard from Antoine again, the different levels of data, L0, L1, L2, and L3. So here you see an overview of where they come in the data chain. So L0 is the raw data that is coming from the spacecrafts downlinked to the ground, and on the ground we do the L0 to L1 processing. So it involves basically two big steps, which is a step that has been historically been called pre-processing, and which is basically responsible for bringing all the time series from different phase meters from different spacecrafts in the same time grid, in the same time frame. And that is then passed on to what is called TDI processing, where the major noises are suppressed. And then this L1, which is a virtually built signal with delays, appropriate delays applied, is then passed on to astrophysical data analysis, from which sources and catalogs are built. So, so these are just a list of parameters that is relevant for these simulations. So 30 centimeter telescopes, 2 watt laser beams, and spacecraft relative motion of 10 meters per second. So these parameters end up playing important part in understanding instrument simulation and the data processing pipeline, as I will describe as we go. So so the content of these of our two working groups, the scientific content, I'll just try to. So by the way, I cannot see the timing, so somebody will have to tell me when there is 10 minutes left. So,
yes, I'll let you know. Yes.
Okay, cool. So basically, to achieve the scientific goals, it comes down to these two constraints: the test masses that are freely falling. They have to have residual acceleration of less than 3 femtometer per second square per root hertz. So this is amplitude spectral density in the LISA observable band. And the interferometry, so the lasers and the optics that are responsible for doing the interferometric sensing, this is between the two optical benches and the test mass to optical bench. The interferometric sensing has to be better, has to have a sensitivity better than 10 picometer per root hertz, again in the millihertz regime. So what you see here is the two test masses that are freely falling in two different spacecrafts, and this is the line of sight and the optical bench that are exchanging laser beams via telescopes. So this is the picometer per root hertz sensitivity that's required in the interferometric sensing, and the test masses that are freely falling along this line of sight to the far spacecraft, this has to be 3 femtometer per second square. So how is that achieved over 2.5 million kilometer? You basically have split interferometry. So you have test mass, local test mass to optical bench interferometer, and then the two optical benches in the two spacecrafts, and then the symmetric optical bench to test mass interferometer. And each of these has to be, requires a picometer sensitivity to achieve the science goals. And because of this 10 meter per second relative velocity between these spacecrafts, because of the orbits, we get heterodyne signals. So unlike in LIGO Virgo, which is homodyne, we have heterodyne signal because the received signal from the far spacecraft carries Doppler shift with it from this 10 meter per second. And actually there's also other there's also other frequency offsets that comes from frequency plan, which I will point out later on. But yeah, basically the frequencies are different. And so you have the heterodyne signal in which these small modulations due to gravitational wave is imprinted. And we will be working in the transponder mode. So because the distance is millions of kilometers, by the time this 2-watt beam comes, arrives to the local optical bench here, it's the level, well, the power of this has reduced to some 100 picowatt. So there's no way to directly reflect this and send back. So we work, yeah, the design of this is in transponder mode for the lasers to be locked to each other. So basically, if you look at the LISA frequency band, in the low frequencies, you're limited by the acceleration noise. That's the residual acceleration noise from the test masses. And then in the mid millihertz to 10 to the -2, you are limited by the interferometric sensing. So it's readout noise, there's shot noise, electronic noise, tilt to length, all kinds of noises. And then in the high frequencies, you are limited by the short wavelengths of gravitational waves that interfere with each other by the time light travels between spacecrafts. So
sorry, Sweta, you have 10 minutes left because you asked. Yes.
Okay, that went much slower. So I will just describe for a few minutes the L0 data and some aspects of pipeline, and I will skip the details in the interest of time. So L0 data is basically on board the long arm signal, which is the interference of the far spacecraft to local optical bench lasers. Then you have the test mass interferometer, which has the motion of the test mass and also the optical bench that it resides in, and the reference interferometer, which is the interference of the two local lasers in the two optical benches in the spacecrafts. So these form the L0 data, which go through, so these analog signals from the photodiode, they go into so-called phase meter that are time-stamped, and then these time series are then transferred to the Earth. So the simulation is basically, yeah, like it's the core simulator of instrument is in LISA node. It's a Python-based graph. So there are atomic nodes written in C++, and the graph is written in Python. And what is simulated are the laser beams. So they're in frequencies. So there are offsets and fluctuations. The fluctuations caused by Doppler shifts and gravitational waves and whatnot. And they have modulations for various reasons to be able to measure, for example, clock noise that will also be competing with the gravitational wave signals. We need to measure it. We're independently using sideband modulation and subtract it in post-processing. And of course, the time frames are important to model correctly as well. So, and this is the conventions that we are using for how to label the lasers, the Doppler shifts, the arm lengths, and etc. So this is all done in, let's say, LISA simulation and the INREP working group. So the L0 data can be written in time series modeled as these quantities. I think maybe I should speed up. So basically you have these laser noises from the far spacecraft delayed by the arm length and the local laser noise, and these are 9 to 10 orders of magnitude larger than the gravitational wave strain. And you have also the optical bench noises, which has amplitude spectral density of like 10 nanoradian per root hertz. And these are also a few orders of magnitude larger than gravitational wave. So we use this TDI algorithm to reduce this clock noise, the laser noise. This is basically using in post-processing already a priori known arm lengths to reduce to reduce the laser noise. This slide basically gives you the core concept of how this is done, and you can apply this to LISA. So these algebraic equations of TDI, they can be transformed into, well, they can be viewed as these geometric paths that are equal arms that mitigate the laser noise. So so this is just in the approximation where arm lengths are unequal but constant, but arm lengths will be not equal, will be time varying. So this is these equations get longer and the path lengths get larger, but basically this works. And we also model the secondary noises. So these are noises that are exacerbated by this TDI algorithm. And then, so that's tilt to length, which is caused by the misalignment of the objects in the path of the laser beams. The relative intensity noise, for example, so the fluctuations of the laser beam in the amplitude that also couples to these phase meter equations, and the clock noise as well. So the uneven ticking of the clock noise is so it's this fraction of clock noise that actually also ends up coupling to the path length that we have to take care of. I wanted to say just a couple of words for pre-processing. So TDI, it assumes, because it's a post-processing algorithm that uses, that needs arm length as input, and it uses phase meter equations measured in different optical benches. These time series need to be synchronized to nanoseconds. And the arm lengths, they need to be known to meter accuracies. So that is what the subject of pre-processing, which is basically a Kalman filter algorithm that gives us, that uses auxiliary data like pseudo-random noise, pseudo-random code to give us the clock offsets that synchronizes these different measurements and the accurate arm lengths. And I think I will, in the interest, speed up a bit. So we also have to take into account the laser locking scheme. So because of the orbits of the spacecrafts, you're necessarily going to have these Doppler shifts of 10 megahertz in the long arm beams. And also because of the limitation of the photoreceivers and phase meter, they're only sensitive in the megahertz, 5 to 25 megahertz frequencies. So this means that we need to lock the 5 of the remaining lasers to one of the master lasers or primary lasers in one of the spacecrafts in such a way that these criteria are satisfied. And so these are the solutions that we have, and we have to implement this also in our data analysis. And I think maybe in the interest of time, I will skip this and come to summary and outlook. So the ongoing—
You still have 3 minutes if you would like.
Okay, I just wanted to leave a couple of minutes for questions.
10 minutes after that, so don't worry about that.
Oh, wait. So I still have—
You have 3 minutes for your talk, and then we can have
okay.
10 minutes of questions. Yes.
Yeah, I misunderstood then. Okay, so I will just talk a little bit about the secondary noises, the tilt to length. So tilt to length is something that it's a coupling in basically a long arm interferometer due to the misalignment of the object. So you have the spacecraft that is jittering in all degrees of freedom, and it couples to the path length by this coupling factor. So if you have, so the local spacecraft jitter couples into the long arm in the local measurement, and also in the same long arm, you measure the remote effect of the, you measure the effect caused by the remote spacecraft jitter as well. And the coupling is so far assumed to be linear, and the coupling coefficient is assumed so far to be non-time dependent. And this is probably most likely true for first approximation, but this linear coupling is quite strong, that it has to be, these coupling factors have to be measured by some experiment, yeah, they have to be subtracted in the post-processing algorithm for the values that we retrieve from this, from such experiment. And clock noise, which is another source of secondary noise. So like I said, these clocks, they are not good enough. Unfortunately, we need femtosecond accurate clocks, and those are not, that's not the case. So in order to reduce in order to mitigate the clock noise, we actually modulate the carrier frequencies with sidebands, such that when you interfere the two lasers, you get carrier to carrier beat note and sideband to sideband beat note. And in the sideband, the clock noise, which is represented here by Q, is magnified, and it's it's transferred to the remote clock. So we need basically additional information in terms of modulated laser beams for mitigating clock noise, and this is it's described in these papers.
1 minute, Sweta.
Okay. So this is just to show some of the results. So if this is the analytical result of how the clock noise shows up in one of these TDI observables if you don't mitigate it. And this is the requirement. This is the 40 picometer basically requirement that we need for the science. And with this additional measurement, we can reduce the clock noise to below the requirement. And this has been also verified in simulation in LISA node and in the TDI algorithm, that this the clock noise can be subtracted to much less than the requirement. And then I just want to end with a list of ongoing studies. So like I mentioned, for TDI to function well, we need synchronized measurements. And it turns out there is not just one way to do this. There's various ways to synchronize, and it remains to be shown, that all these results really yield the same level of L1 mitigation that you expect. So these things, this is ongoing study. We do have a baseline, of course, for the INREP pipeline of how to take this into account. But yeah, there are other methods as well, and that's ongoing studies. And then there's the question of glitches. So we will have gaps and scheduled gaps, but also unscheduled and unknown gaps and glitches. And these have to be modeled a bit more realistically, maybe not for MFR, but post MFR, this needs to be looked into a bit more detail. And there is a group called Artifacts within LDPG that are looking into this and how this affects the parameter estimation and so forth. Then there is, for the INREP pipeline, we have to look, so the various noise mitigation is done by defining different processing elements. So laser noise subtraction is one processing element. Optical bench noise suppression is one processing element. And so is clock noise suppression and tilt-to-length suppression, and there will be more processing elements. So in which order these suppression processing elements should be done. This is also something that we are studying, the effect of the frequency planning. So I talked about how we have to use this locking scheme, and there's various ways to lock. And it's not that if you find out the effect of one of the locking schemes, what is the effect on the TDI signals, that gives you an overview of all the locking schemes. So they have to be studied and looked at independently, and the secondary noises, how they are affected by this frequency planning. And there's of course a lot more going on, but these were just some of the things I wanted to highlight. I think I'll stop with that. And
okay, thank you very much. Excellent. Let's thank our speaker. If you want, with your camera or just reaction on the Zoom.
I am trying to look for.
So in the meanwhile that Sweta is preparing the slides, we have around 6 minutes or 5 minutes for questions and discussions. So I'm going to read some of the questions so that some of the audience asked. One of them is that, what is the timeline for choosing a laser locking scheme?
Oh, sorry, what?
What is the timeline for choosing a laser locking scheme?
What is meant by timeline? Like how often we have to apply the locking, or?
Well, let's maybe the.
I don't quite understand what is meant.
Maybe I'll go with the next question, and the person who asked can clarify there. So another question is that how severe are the requirements for temperature stability in the instrument for obtaining the required timing or / phase resolution?
So this, of course, there are requirements for the temperatures inside the spacecraft, but actually this is not something we are looking into that detail for the LISA simulation. And INREP, maybe there is someone in the group who can answer this, that has effect for the test masses. And but in simulation, we're not looking in the simulation working group and in the processing pipeline. We're not looking at this right now.
Okay. So I remind you, you can ask your questions here in the Zoom or on the Slack. So regarding the timeline, apparently the person who asked was mentioning when it will be determined. I mean, when it will be fixed. Is it going to be fixed before the launch?
Oh, yes. So this is, of course, this is going to be fixed before the launch, and it will be uploaded on the phase meter or on the computer, and yeah, it will.
Okay, great. If you have any further questions, please mention them in the chat, the Zoom, or on the Slack. You still have maybe 2 minutes or 2-3 minutes for questions or discussion. Another question is that, can we change the scheme, this timeline during the mission if needed?
Yeah, I think so, because you can telemeter it and you can change this according to, but why you change it has to, yeah, whenever you change something, then there is a disturbance in the, there might be a data gap, right? So there has to be good reason for that. But I think the idea is to have one frequency plan that really optimizes the signal to noise ratio for most of the sources, that minimizes the noises. Yeah.
Okay, thank you. So we have time for one probably or two quick questions. One question is that, how can I learn more about TDI works?
So there's lots of literature out there. This TDI is known for 20 years now. So there's, yeah, you can look for the literature, or I can also, yeah, you can email me and I can point you to some good literature that explains the core concept of TDI.
Perfect. Thank you very much. So